The role of engineering decision-making immerses in the process of stress analysis. Engineers need to make decisions at every step, from the given conditions to the calculated results of the simulation. Usually, the given conditions are not directly known or absolute for an engineering problem. Depending on the purpose and resources of the analysis, an engineer decides the given condition. You will need to make decisions for geometry. The geometry can be created as detailed as possible, but is it necessary for the problem? You will need to decide what kind of materials model should be used for a different part of the problem. You also need to tell what the appropriate load and boundary conditions are to represent the realistic condition for the problem. Besides this, if there are multiple bodies in one problem, you might also need to determine the connection between them. Should it be considered as contact or joint? What kind of contact or joint is appropriated? In fact, it's very rare that we can bring a given problem to simulation directly without engineering thinking. Let's have a look at a more complicated problem. A mechanical simulation is needed for the study of the lumbar section motion. An engineer needs to make decisions for such questions. Given the geometry file from 3D scanner of lumbar, what details need to be remained and what can be ignored in solid mechanical analysis? What's the connection between the different parts? What material should be used for the vertebral bodies? What should be used for the intervertebral disc? It's a complex loading condition for the lumbar part. How can we reflect that in the analysis? As for the fine part, solid mechanical analysis finds results everywhere over the body. These results include deformation, stress, strain, reaction force, etc. With these results, an engineer can make informed decisions on what is expected and what is not, so that you decide how to improve design to meet the requirements or reduce cost. In this lumbar section problem, engineers can identify high-stress area. Such information can be used to determine if spinal spacer is needed or how the spacer should be customized. Let's have a look at another example for engineering decision-making after the results are obtained. The problem we're solving is the pitch arm of a helicopter rotor, which holds the blade in rotational motion. With boundary conditions and loads on the part, the maximum deformation result is about 0.46 mm. If this amount exceeds the design requirements, an engineer needs to consider change the design so that the deformation can be reduced under the same load. One way to do that is to add stiffener for the arm so that the stiffness is enhanced. As you can see, the deformation result of the new design is reduced as expected. While traditionally it is the engineer's role to dictate the shape of the structure, now with advances in technology, the computer can help to tell us what the best shape is. This reverse design process relies on topology optimization technology. Due to the free form of the geometry from topology optimization, this technology is mostly used in 3D printing or customized manufacturing.